Hi, everyone. Thank you so much for joining us here at PyLadiesCon 2024. We are really excited to have you here joining us today. I am very elated to be able to introduce our next speaker. Our next speaker is in the person of Aisha Yazur. Aisha is a recent graduate with a bachelor's degree in computer science. She is also passionate for blending AI innovation with ethical practices while advancing AI technology. Today, will be giving us a talk on the topic preserving privacy in AI, techniques and tools for secure machine learning. Everyone, please help me welcome Aisha Yazur on stage. Thank you. I hope you enjoy the session.
Hello, and a warm welcome to everyone tuned in. I'm Aisha Yasser. I'm very excited to be with you all here today. Before we deep dive into today's topic, a bit about me. I have graduated with honors in computer science and have an experience as an AI engineer. My academic and professional journey is driven by a passion to meld artificial intelligence with ethical integrity and building sustainable solutions. Today, I'm absolutely thrilled to be here at Pi Ladies Conference to discuss a topic that lies at the heart of modern technology: preserving privacy in artificial intelligence. With AI, we're diving deep into data like never before, and that raises big questions about privacy. So let's get into how we can keep pushing AI forward without stepping on our ethical responsibilities. We'll unpack the techniques and the tools that keep AI both powerful and respectful of privacy. Alright, so let's lay out our roadmap for today's session. We're going to kick things off by discussing why preserving privacy in AI is absolutely critical. We'll then ease into a brief introduction to machine learning, the engine powering today's AI revolution, making sure everyone is on the same page, whether you're new to the concept or a seasoned professional. Next, we'll pinpoint the key privacy goals essential for integrating AI into our lives responsibly. From there, we'll dive into three powerful techniques that can be used to safeguard privacy in AI models: differential privacy, federated learning, and homomorphic encryption. We'll unpack each of these methods, exploring how they work and their significance in the AI landscape. Finally, we'll wrap up with some key takeaways and a call to action. AI's influence is pervasive and profound. It's reshaping diverse sectors from streamlining patient care in healthcare to predictive diagnostics to optimizing crop yields in agriculture via precision farming. AI's benefits are undeniable. However, with AI, we're diving deep into data like never before, and that raises big questions about privacy, like its reliance on data, particularly sensitive personal data, poses substantial privacy risks. In an age where data breaches are increasingly common, the consequences can be severe as it can result in exposing individuals to privacy violations and organizations to legal and financial repercussions. Recognizing these challenges, global regulators like the GDPR, which is the General Data Protection Regulation, and CCPA, California's Consumer Privacy Act, have set strict privacy benchmarks. These regulations mandate that we, as developers, researchers, and stakeholders, integrate robust privacy measures at the core of AI technologies. So it is essential to know how can we harness AI's potential responsibly, safeguarding the privacy of individuals while continuing to innovate. At its core, machine learning is about enabling computers to learn from and make decisions based on data. Unlike old school programming, where we had to spell out every little instruction, machine learning lets computer learn from data to make decisions and spot patterns all on their own with minimal human input. The journey of machine learning starts with data, massive amounts of data. This data fuels algorithms that adapt and improve over time, enhancing their predictive accuracy. These capabilities are foundational to applications such as facial recognition, autonomous driving, and so on. As we progress, Machine learning continues to evolve. Early models, which were simply relatively linear, have given way to advanced neural networks and deep learning techniques, which are capable of handling tasks of incredible complexity. A few key types of machine learning are supervised learning, which teaches computer to make predictions based on past data; unsupervised learning, which helps them find patterns in data; and reinforcement learning, which lets computer learn through trial and error. Let's shift gears and talk about the key privacy goals in machine learning. It's not just about the cool tech, it's about making sure the tech respects our privacy. First up, we've got identity privacy. We're not just hiding names, we're making sure that the data cannot be traced back to anyone, even indirectly. Then there's raw data privacy, which is about keeping the actual data under wraps from anyone who shouldn't see it. Then comes feature and model privacy. Here, what it means is that we need to protect the details within the data and models themselves before clever folks can sometimes reverse engineer them to get at private information. Last, there is input privacy, which is about protecting data as it's fed into real time systems. It's about making sure that the data remains a closed book, only readable by those who can really need to know. Together, these privacy goals create a robust framework for privacy preserving machine learning. And this ensures that the technological advancements do not come at the cost of privacy and ethical integrity. These are three privacy preserving techniques that will be explored in the upcoming slides. So, first up, let's explore differential privacy. This is all about adding a bit of noise to our data analysis processes. Think of it like a bit of fuzz on a radio signal, enough to keep anyone from picking out individual tunes, or in our case, personal data. Okay, let's consider a practical scenario. A database containing employee salary within an organization, and analyzing such data for average salaries or identifying pay disparities can pose significant privacy risk. How can we derive useful insights without exposing individual salary information? Differential privacy. Differential privacy offers a solution by introducing a mechanism to add controlled, random noise to the data or the analytical queries, and this noise is carefully calibrated to mask the influence of any single individual's data on the outcome. For example, when computing the average salary, instead of deriving an exact figure, the differential privacy mechanism would adjust this figure slightly by either adding or subtracting a random amount. This adjustment ensures that the presence or absence of any one individual's data in the dataset does not significantly influence the result. Thus, even someone with knowledge of all other salaries cannot accurately determine any single individual's salary from the published data. So it's a clever way to balance a scale between using big data and respecting individuals' privacy, ensuring we can all benefit from insights without sacrificing confidentiality. Incorporating differential privacy into machine learning involves several strategic integrations across different stages of the process of data handling and model tuning. First is the data collection stage, where by introducing noise to the raw data, we begin the privacy preservation process early and set a strong foundation for subsequent analysis. Secondly, is during a model training phase, where we can tweak things like the learning rate in algorithms to keep the data under wrap. And thirdly, well, lastly, we can apply differential privacy post training when the model is trained. So, adding noise to the model's output or even its parameter before they're used or published can further secure the privacy. This ensures that the model, when deployed, does not leak privacy through its predictions. However, the integration of differential privacy is not without challenges. The primary challenge lies in the trade off between privacy and model accuracy. more noise, which generally implies better privacy, but it can reduce the accuracy of the model. Managing this trade off is crucial and involves careful calibration of privacy parameters such as the privacy budget, which measures the degree of privacy or information leakage involved in the process. Tools like TensorFlow, Privacy, Opacus, and PySift help us find that sweet spot, keeping our models useful and our data private. And we can easily integrate differential privacy techniques with existing machine learning workflows, effectively using these libraries. Differential privacy is being utilized by some of the biggest names in technology, as here listed on the right hand side. For example, Uber. It implements differential privacy to safeguard both drivers and riders by limiting the amount of personal information that's accessible to data scientists. This ensures that travel patterns and individual behaviors cannot be traced back to specific users. Next up is federated learning. Think of it as the democracy of data. Instead of all data traveling to one central model, the model travels to the data, right where it lives on user devices. This is known as decentralized training of models, which is training models directly on devices where the data is generated, such as mobile phones or tablets. Let's understand this with a practical scenario of federated learning. Imagine hundreds of mobile phones, each learning from their users' typing habits. Here what happens. Each smartphone locally analyzes how its users types, everything from commonly used words to sentence structures. This data is used to make small, crucial improvements to the device predictive text model without ever leaving the phone. These local updates are then sent back to the central system and they're aggregated and non revealing. It's learning from you right on your device, and only the lessons, not the specifics, only the lessons get shared to improve the model. This approach isn't just good for privacy, it's also great for cutting down on data traffic, which is perfect for real time application. It's a win win, keeping data private and processing snappy. Applying federated learning within machine learning frameworks presents a unique set of advantages. The core benefits of federated learning and machine learning is privacy protection because data stays on the local device and you're only sending model updates to the server. Then there is reduced latency since the data does not need to be sent back and forth between the device and a central server. So the response time are much quicker. And last but not least, federated learning is exceptionally scalable because it can handle data from thousands or even millions of devices efficiently. However, the implementation of federated learning do pose significant challenges such as of data heterogeneity, which is the varying nature of data across different devices that can lead to inconsistency in models' performance. And secondly, there is a need for continuous communication between the devices and the central server, and this can consume substantial network resources, leading to communication overhead. Google Gboard is a prime example of federated learning, which is being applied in real world context, and it works in the similar manner to the example which was presented in the previous slide. The virtual keyboard app utilizes federated learning to improve predictive text and autocorrect features without compromising privacy. Tools like TensorFlow, Federated, PySift, and Flower provide the perfect toolkit for integrated federated learning into our machine learning projects. Moving on to the last but not the least, a privacy preserving technique in our presentation is the homomorphic encryption. This technique allows computations to be performed on encrypted data, thereby enabling the encrypted data to be directly usable without needing to decrypt it first. With this technique, we can work on sensitive data without ever seeing what's under the hood. It allows sensitive data to remain secure throughout the computational process. Okay, to grasp how homomorphic encryption functions, think of it as an advanced form of public key cryptography. Normally, data encrypted with a public key can only be decrypted with a private key. Homomorphic encryption takes this step further by enabling complex calculations on this encrypted data. What is the result? When decrypted, the outcome is exactly as it would be if performed on the original data. Okay, let's take an example. Consider a healthcare organization which is using homomorphic encryption to train machine learning models while keeping patient data confidential. The organization will encrypt patient data and send it to researchers who perform analysis and model training directly on the encrypted data. And this process ensures that the sensitive information remains secure and patient privacy is maintained throughout. So, with this technique, whether it's bank analyzing encrypted financial data or healthcare providers which are crunching encrypted patient stats, the data stays secure from start till the finish. When we bring homomorphic encryption into machine learning, we're looking at a setup where data privacy is locked down tight. From training data to real time prediction, everything remains encrypted. This ensures robust data privacy and compliance with strict security regulations. It also offers secure outsourcing of computations to external resources like cloud services, but it also introduces challenges such as increased computational complexity and potential limitations in operational efficiency. Python libraries such as Stencil, PySeal, PyHeal, and Petlib provide these essential tools through which we can integrate homomorphic encryption into our machine learning workflows. To wrap up our exploration of privacy preserving techniques in machine learning, this slide review how each method aligns with the privacy goals we've outlined. Each technique, differential learning, federated learning, and the homomorphic encryption, has its own strengths and meets different sets of privacy goals that were discussed earlier, whether it's protecting identities, securing raw dataset or the feature dataset, or ensuring privacy of inputs and models. Choosing the right technique depends on several factors, such as the specific privacy need of your data, the volume of data that you're handling, and the level of privacy that is required. It's about selecting the right technique for the job, so it's on you. Advanced Python libraries play a critical role in making these privacy preserving technologies accessible and effective, and these tools were explored under each of the technique, which are available currently in the market. The benefits of adopting these privacy preserving techniques are manifold. They help ensure the confidentiality of sensitive data, align with the stringent global privacy regulations, and allow for secure collaboration across different sectors. So, by integrating these techniques into our AI systems, we also support the broader goal of ethical AI, ensuring our technologies are developed with a strong moral framework that respects users' privacy and it promotes transparency as well. As we continue to advance in the field of machine learning and AI, it is imperative that we remain committed to these ethical standards. Our technology should not only drive economic and technological growth, but it should obviously also reflect our core values of privacy and responsibility. Every dataset, every model, and every prediction is a chance to do it responsibly. So I urge all stakeholders, from developers and researchers to policymakers and industry leaders, to embrace these techniques, and together let's continue to innovate responsibly, ensuring our technological advancements benefit society as a whole while safeguarding individual rights and privacy. Thank you all for your attention and thank you for joining me today.
Thank you so much to Aisha for sharing your knowledge with us on preserving privacy in AI. And I hope we all enjoyed our session with her. Thank you so much once again, and see you on the next session. Bye.